Hey everybody, welcome back to our next lecture on electromagnetism. I think this is part 4. What we're going to look at today is that we're going to look at types of circuits, single and parallel circuits, and we'll also look at Ohm's law. Okay, so let's go ahead and dive into it. So let's look at a series. Now, a series circuit is kind of like if you have all your like light bulbs or all like your resources that you're trying to light up, they're all connected into what we call a single loop. And so we're going to explain this in a little bit. But the first one is called a series circuit. And so let's say you have all these like a very cheap Christmas lights that you bought, and if one of those lights happen to go out, the whole strand goes away. And so if one bulb goes out, the whole thing goes out. And so that's what we call a single path. And it looks like this. Okay. And so let's say that you have your power source, which is like a battery. Okay. You have your battery. It doesn't have to be a battery. It could be just a light switch or a plug. A plug can have, things like this. But anyway, a power source. And so you have a light, and a switch. So a switch is kind of like you're on. It's like this on off business, right? So you're going to do off and on, and it's like you're going to walk into your house and flip on the lights. But what you're going to do is that you have one light bulb and two light bulbs, and they both draw out a resistance. So these are called like resistors. Okay, they're a resistance. A resistance makes light. And so what you're doing is that obviously this switch is in the off position. The reason it's off because it's not connected. But as soon as you click it on, which is in the on, what's going to happen? This whole thing is going to move down there, and what it does, it completes this circuit. So it completes this circuit, and the current runs around the wire, into the other terminal of the battery, and obviously these lights are on. So what happens is, what if I unscrew one of these lights? Well, you know that from the following, the whole thing goes out because there's nothing to connect. And if I shut this off, click it off and then make this little gap, there's no current. Okay, so that's what a series circuit is. Okay, and what's going on is that if you take all the voltage, so take off all the voltage. So let's say this was a 6-volt battery. And if I take this plus this gives me the total voltage with the total resistance. And we're going to talk about this later. And what you're doing is that you're just adding stuff up. This is all it means. That this might not be making sense to you. That's okay. But think about this. Since this is single, you're just going to add this plus this gives you the total. Okay. So if you add up 3 batteries, or sorry, not 3 resistors or 3 light bulbs, you're going to take this plus this plus this. And the more you have, the more you're going to add. That's what this means. This is that sigma notation we talked about. Okay? And so this is kind of what's going on with all this. And so if you add up all the bulbs, they become dimmer. And the reason they become dimmer because this voltage has to come across to all these here. And so if it's going in this fashion, this first light bulb is going to have so much current, so much more light than, let's say, a last one here. And so if you ever have a Christmas lights, the reason Christmas lights are not that long is because they require the same amount of current that flows through them. And so you got to be careful on the length that you're getting of Christmas lights. Okay. And there's always pros and cons to everything, right? So the cons is that you have limited control of this, because limited control, well, you only can hook up so many until it's gone. And then all of a sudden, if you take one out, the whole strand goes dead. The pro, they're very cheap to have. And I think what I'm trying to mention there is that they are cheaper to have, but you have not a whole lot. So what else do you have as a pros? But you have it on a single switch. I mean, it's not a lot. It's not a lot. Not a lot of wire. It's like a single wire, well, a single wire area, just a single wire. And so it's very easy to set up. So I should say it's very easy to set up. Okay. So that's what we call a series circuit. Now there's the second one. This is called the parallel circuit. Okay. In parallel, if you think about your geometry, parallel lines, okay, a couple of lines like this. I think in geometry they had something like this. That means they never intersect. And so in parallel, you can have a power source like a battery or plug, but there's multiple paths for that current to flow. And it's simultaneously, it's over and over and over. But the kicker is, not the kicker, I guess it's a pro. If one path of the current fails, you still have current. And we're going to learn about that right now. So here's your setup. This is how your house or apartment is set up. Because in your house is that if one of your plugs, let's say one of your plugs goes bye-bye in your walls, it's not going to affect the whole system. So if I turn on one light, the other light can still go on. And so it just has a lot more wiring that you got to worry about. And so let's say you take a power source and you got the current's flowing, current's flowing, current's also flowing, current's flowing down here just as well. Current's flowing, current's flowing all the way back here, right? And so each they call them branch. They call like a branch of a tree. So if you think about like a tree has all these branches, each branch, each one of these has the same current flow, the same current, same current flow. Sorry, there, same current flow, and that's what happens. So if let's say this one got cut, I can still have current that runs through this. But what if all three of these were cut? Well, then there's no current. So the idea with this is that if you take each branch has the same source, like a light switch, the pros is that if one goes out, not all. The con of this is that there's so much more wiring and it's safer to maintain the voltage. Now, that might not be a bad thing, but in your house, there's so much wiring going on. It just makes your mind just like, oh my God, these guys are good. And so what we're going to do today is kind of go through some examples and see what both of these require. Okay, so let's go through this and see how it goes. So we're going to go through this the series circuit first. So here we go. So this is called the series circuit, and so we have our source. You might have to stop the video and write these down in your notes. I might be kind of fast on these because time is a lot here. So this is called a series circuit because I hope that you kind of see the abbreviations of the 9-volt power source. A lot of times they will put a positive and negative. This is to represent the battery. So this is to represent the battery source. This is the wiring. And if you see these little squiggly lines, they look like this. That means these are called the resistors. These are called the resistors. And what resistors are doing, these are just kind of like your light, like the light bulb. It's the light. And so what these little symbols are, don't worry too much about these symbols too much, but this is just a symbol for resistance. Okay, just a symbol for resistance. Usually voltage is with the V, and the current, if you have current is the flow. So this is like the flow. That's represented by I. And so you got this setup here of V, resistors, and this. And we're going to talk about what we, in a little bit, called Ohm's law. Okay, we're going to talk about Ohm's law just a little bit. But let's take care of this. So let's say we hook up two resistors, 3 resistance. We have a 9-volt battery. Maybe your first question comes up on your homework that says, what's the total resistance? So the total resistance is what you're going to do is what? You're going to take 2 plus 3. 2 plus 3. And that's just kind of how you're going to write it to explain it. And if you go 2 plus 3, well, the total resistance is 5. Okay, 5, resistance. I think it's 5 amps, but we're going to talk about that right now. Let's just make it simple for you. Okay, so just add up all of the resistance around. So if you had another one here, another one there, another one there, you're just going to add up all those numbers. We get the total resistance. Okay. What if we want to find the current? The current of the circuit. So the current is the flow of electrons through around. And so what you're going to do now is you're going to actually use what we call Ohm's law. So Ohm's law is just kind of it's kind of a mathematical representation. And what that means is it takes your voltage equals the current times the resistance. So this is voltage, this is the current, and this is resistance. Okay. If you're going to be an electrician or somebody that works with this kind of stuff, you should know Ohm's law. It really does help you understand how much voltage to resistance that you're going to use. So that might be an electronical thing that you might want to pick up. So I want to find out the current of using Ohm's law. And so I'm going to use this. V equals IR, but we want to solve for I. Because we want to figure out what's the current. We want to figure out the flow. We want to figure out the flow around here. We don't know that. We know we have a 9-volt battery. We know that we have 5 resistors. 5 resistance. So what you're going to do is you're going to take your lovely Ohm's law formula and you're going to solve it for I. Because you're trying to figure out the current, which is V over R. So what's the voltage? The voltage is 9. And what's the resistance? 5. And so if you do that, you get 9V divided by 5 resistance. You get 1.8 amps. Now that's what the current is. So we measure. So a lot of times it's called amps or A. And amps is the determination of how much current flows. So a big thing about this, if you ever had an electric fence, if you know what an electric fence is, it kind of goes on a big farm like this, goes like it makes your perimeter, and it keeps in the cattle, all kinds of animals and stuff like that. Maybe it gets people away from it too. But if you ever touch an electric fence, it doesn't do too much to you. It's going to sting a little bit because it has low amps. There's low amps, and it doesn't do anything to you. But the higher the amps, so think of it this way, the higher the amps, the more deadly. Okay? So now we're going to figure out another thing. What if we want to figure out the voltage drop across each resistor? So let's go back up to this. Each resistor requires a certain amount of current, right? So think of it this way. If we hook up a 9-volt battery, that means this has some of that voltage and this has some of that voltage being used. We want to be careful because we want these resistors or light bulbs to be working properly with our source. So I want to figure out how much voltage you're using and how much voltage you're using because it matters. Because if you put another light on here, it might not be as bright. So here we go. So we're going to take our information and we want to figure out what we call the voltage drop of each resistors. Now, since there's 2 and 3, we have to do them separately. And to do that, we're going to use Ohm's law again. But what do you think we have to solve for? We're looking for what? Voltage across. So we're going to use this whole thing, but we're going to kind of use this stuff here too. So let's do it. So using Ohm's law, which is V equals IR, you're going to take each resistor that we found on the front, and you're going to do voltage of 1 and voltage of 2 using this. So I think the amps were what, 1.8? Yes, the amps were 1.8. If you look back, that was 1.8. And oops, you got 2, which is that 2 resistance. And if you multiply that together, you get 3.6 volts. Now take the resistor 2, and we're still going to take the same amps, and we're going to multiply that by 3 resistance, and we got 5.4 volts. Okay, do you see how that's going? Now, let's say that you're kind of on the job. Maybe you want to check that, hey, is my math correct? If you take this number plus this number, what do you get? Don't you get 9 volts? And what was the battery that we had on the front? 9 volts. So that's how you can tell how much volts these are taking with what you have. So let's say you wanted to hook up a third light. So you want to hook up a third resistor. You want to know some stuff about it. Okay, because you're already using 3.6 and 5.4, but if your third one used 4 resistance, this is going to be a lot lower. You're going to have to go back to the beginning. Okay, let's say you wanted to draw the path of the correct current in the diagram. Usually it goes from positive to negative. Okay, it usually goes from positive to negative, so it kind of goes in this fashion. Okay, so I hope that made a little bit more sense with that. Why don't we look at a fuse? So in your house, you have what we call fuses, and you might have. You can probably figure these out. You can kind of go to your fuse box outside your house, maybe then the side of your apartment or something like that, and they do blow out, and you have to go click them on. So I don't know if you ever did this before, but they're a big old. So if you go on the side of your house, looks like a little box like this. It's a metal box, and they should have like a little lock right here. You go out there and you open it up, and it has all these little. They're like black switches, and a lot of them are maybe with oven or dishwasher, living room. So they all have a fuse. And so what that means is that what if we had, your house uses about 120 volts from the house that comes in from the power lines, right? And so let's say that we had a current that uses about 1700 watts. Let's say you have a hair dryer. And then you have a 600 watt coffee maker that's connected to a 30 amp fuse. And if you don't know what fuses look like, there's a couple pictures of them, but they kind of look like this. And so current flows into here, and then it flows out here. You might want to grab one. This looks like fuse. This is like a fuse. There are all kinds of fuses that you can find in your car too that maintains this, but you can kind of Google it if you want. So let's say you had 120 volts. You had 2 things hooked up with a 30 amps. What I'm going to ask you, what if you put both of these on at the same time? You're blowing your hair and the coffee maker is making your lovely coffee. Are you going to blow the fuse? So here's what we're going to do. We're going to use kind of like Ohm's law in a way. If you think about it, this is Ohm's law. I just changed the P to power because we're doing watts. Watts is a different kind of measurement. And so if you're kind of tricked on there, you use a certain amount of power. It's just mean power, and they're in watts. This is called watts. Okay, and so it's very simple to Ohm's law. You can look that up if you want. I don't know if you're convinced yet, but so what's the power in my hair dryer? How much power am I using really? And so what you're going to do, you're going to take both of these, and you're going to say, okay, here's my hair dryer. It uses this much watts. I mean, hair dryers use a lot of wattage. This is why sometimes the power it goes dim, your lights go dim. You're going to take 1700 watts, divide it by how much is coming in. 20 volts. You're using 4.6 amps. The coffee maker uses 600 watts. You're going to take 600, divide it by 120, and you have 5 amps. What you're going to do now is that if you take the total of this one and this one, you get 19.6 amps. But what is your fuse? Your fuse was 30 amps. So is that close to 30? No. So you're not going to blow the fuse. You're not going to blow the fuse. So let's say your homework, let's say that this number, the number of amps, was greater than 30. If it's greater than 30, you're going to blow the fuse. Do you see kind of what you're doing? I hope you do. Because don't overthink this. But you're going to take whatever you're using, add those up, and depends on how much your fuse can handle. This is why your fuses blow out in your house. You have to go click them on outside. They do this. So that's what fuses are and maybe how this is working out. So let's talk about parallel circuits and we're done. This is going to be a little bit of a longer lecture, sorry. Let's talk about parallel circuits. Parallel circuits is like what we discussed, right? You're going to take let's say you take a 12-volt battery and you have each branch, but they don't always are going to be the same. I'm doing this because it makes it easy for us as you're watching this because you don't go too much into this, okay? These don't have to be the same. I made them the same to make our math easier and quicker. But if they're different, if these are different, you're going to have to do this again. And I will show you. So here's your circuit. So this is parallel. Why is it parallel? Because you have a branch here and a branch here. And if this branch is shut down, you will still get current. So there's 3 ohms here and 3 ohms here in your 12-volt battery. So here we go. Here's our first question. What is the voltage across each resistor? So how much voltage is this guy making? How much voltage is this making? Since these are the same, is it okay if I can just do one voltage, which is 12 volts? Think about it. How much voltage is going across each resistor? They're just 12. It's just using 12. What if these were different? Don't worry about it. They're still using 12. If you add another one, and another one, they're still going to use 12 volts because it doesn't matter. They're all using 12 volts. Okay, what about the current? Remember, current is how much is being used from the 12 volts. And that's what you have to figure out. So how much current, how much voltage are you using? Well, you're going to do this. It says each branch. So what if these were different? You would have to do this again. You're going to use Ohm's law again, which is V equals V over R. And you're going to go 12 volts over 3. And since these are the same, you don't have to do this again. So, for example, what if this was a 2? If this was a 2, you would have to do what? I equals 12 over 2. So if this was different, you would go 12 over 2. Okay, just to make sure. For if this was a 2. But since these two are the same, I said the same, you don't have to do this twice. Just saves you some work. And you're going to get 4 amps. So each of these use 4 amps. Okay. So now, what's the total current provided by the battery? Okay. Well, if you take both resistors, you add 4 plus 4, you're going to get 8 amps, right? Because you're going to take this plus this gives you 8 amps. Okay, so that's the current that you're using. That's the I. Next question. What is the total resistance? So what's the total resistance this one and this one are using with that 12-volt battery? So you're still going to use I equals VR, which is that Ohm's law piece. And now what you're going to do, you're going to solve, it says, what's the total resistance? Well, you're going to take the resistance, which is R equals V over I. You're just solving this equation for R, and you get 12 volts over 8, because 8 was the number of current provided by the battery of the two resistors. You have about 1.5 ohms. Okay, and so that's the idea of all this. Let's say you had some more questions on this. You just have to do some more of this. You have to figure this part out as you go. Just the takeaway from this is just remember a couple things and try not to get all anxiety on this. Series circuit, you're just going to add them up. Parallel circuit, you're going to have to do them each individually. Depends on if they're different. And you're just going to have to know this Ohm's law business. Okay, V equals IR. How do I remember it? I just kind of remember it as this. Sometimes they might have a little triangle that looks like this, and this is V equals IR. And usually what happens is that if you want to solve for one of these variables, you think of like you think of division here. You want to solve for this this is division. Now, I don't like this. I don't really want to give this to you because I just don't want to upset you with the memorization of this. But if you ever Google Ohm's law, if you ever Google this, it would give you this triangle to remember. I am not going to have you do that. I'm just going to have you remember it. V equals IR, and then you have to solve for what variable you want. Okay, so you take it as you want on that, and don't overthink it, and try the homework out and look at the answer key. All right, I hope this works, and just keep going, everybody, and I see you when I see you. All right.